Okay, are we live? Hi everyone to Fiveable Chemistry Crams 24. To be going over unit 4, and this is one of the 5 nights. We had a bit of a roster day, but hopefully everything will be fine tonight. My name is Kritika. I'm one of your student hosts. I'll be presenting the first half of the presentation today, and then we'll have Yash, another student host, present the other half. We also have some other hosts and teacher hosts in the chat who are going to be here to answer any questions that you may have. So once again, tonight we're going over units 4 and 5. We went over units 1 through 3 yesterday. If you missed the cram, that's totally fine. There will be a recording posted under the same link soon. I think it should be up by now. And tomorrow we're going to be going over units 6 and 7. On the 4th, we'll be going over units 8 and 9, and May 5th will be our So this is how you can make the most out of tonight's cram session. So first of all, we would highly recommend taking notes. It will keep you active, an active listener, and make sure you're retaining the information that you want to. I'd recommend writing things that you know that you've struggled with before in the past, or something that you want to make sure you remember for the AP exam. But just don't try to write down everything that we're saying or everything on our slides. The slides will be available to you after the break. After this cram, so you can go back and rewatch this cram. Next, we're going to have a My Stuff tab. So it's going to have all the slides and replays for you. So once again, you will be able to see everything after the cram, right after the cram, actually. Next, we have our group chat, which is our chat function. So it's going to be a really great resource for tips, tricks, and to participate when we ask questions. In the chat, a lot of our other student hosts will be there to answer any questions that you guys have during the cram if I'm not able to see them. And you guys can also just interact with each other, share your own tips and tricks, things like that. Finally, we have our Q&A tab, which is another really helpful feature. So this is going to be for asking any question at all, preferably about the content. So you're going to want to check the comments on the Q&A for any answers that one of the hosts write down. Yes, we will be taking breaks. We are not going to be lecturing at you for a whole 3 hours. We'll be taking breaks to make sure that you guys can go up, use the room, get some water, get some food, and just give your brain a bit of a rest. The replay will be available immediately after event in My Stuff, just like I've said. And we can go on to the next slide. Make sure you follow at ThinkFiveable on all of our socials. We have on LinkedIn, YouTube, TikTok, Instagram. Show us all your love, and yeah, make sure you follow us. Next, we have our community agreements before we get into the crams. So we want to make sure that everyone is being supportive of each other. Let's lift each other up. We're all here to study for the cram, for the AP exam, and so is everyone else in the chat. So make sure that we're being supportive of each other. Next, be patient. We have 5 nights together, 1 down, 4 left to go, and we'll be able to get to all of your questions and any part of the curriculum that you're confused about. Finally, be kind to one another. We're all real people. That includes us, the student hosts, the teacher host, as well as those in the chat. All right, so this is our agenda. So we just went through the welcome, and we're going to go into some chemical reactions, then kinetics, and then we'll have a practice. And then at the end, we'll have a Q&A session, and then our closing. So first, we're going to start off with Unit 4, Chemical Reactions. So this is going to make up around 7 to 9% of the exam, so it is pretty important. And once again, reminder, if you have any questions during the cram, make sure to put it in the chat, and one of the other hosts will get to your questions. So these are the topics that we're going to be going over. We have foundations of chemical reactions, net ionic equation, representations of reactions, physical and chemical changes, stoichiometry, introduction to titrations, types of chemical reactions, introduction to acid and base reactions, as well as redox reactions. All right, so we're going to go over all the types of reactions real quick. So we have synthesis, which is when you have a molecule A and molecule B, they react and they come together to form AB. They are now chemically connected. So that is your synthesis reaction. Then, as the opposite of a synthesis reaction, we have a decomposition reaction. So that's when you have AB and it splits up into separate substituents. So it's going to be A plus B. Next, we have our single replacement. So this one's a fun one. We start off with AB bonded to each other, and then we're going to add in our friend C. So C comes in, it kind of knocks B off from its spot, and then it comes in and it bonds with A instead. So we're going to end up with C in the spot where B was, and B is going to be in the spot where C was. So AB plus C yields B plus AC. Next, we have double replacement. You might have also heard of it being referred to as double displacement. Same thing, different names. So this is very similar to single replacement, except instead of starting off with C as just its own alone, like molecule alone, it's going to be bonded to something else. So we're going to call that D. So we have AB, CD, and then what's going to happen is B and D are going to kind of get off of their original bond, and they're going to switch places. So we end up with AB plus CD yields AD plus CB. Finally, we have combustion, which is when you add any hydrocarbon and you react it with oxygen, and this will leave you with some amount of water plus CO2. So something that's really important for combustion as well as all the other reactions is making sure that your stoichiometry is correct. Finally, we have an example here at the end. What is this reaction? So what reaction do you guys think HCl plus NaOH yields H2O plus NaCl is? Give it a couple seconds, guys. All right, we got some people saying displacement, double replacement. Let's see what the answer is. Next, yeah. So this would be a double replacement. Could we go back? So this double replacement, it technically is acid-base as well because you are taking an acid and a base and reacting them to get water. But more generally, this is a double replacement as well. So you can see that H is in HCl is kind of taking the place of Na, and vice versa. Okay, next slide. So now we're going to go over types of changes. So first off, we have physical change. So this is a change to the physical characteristic of a material. It doesn't really have anything to do with the chemical characteristics. So these changes will be things like mass, texture, shape, temperature, and matter, that as long as it's still the same, it has the same chemical composition. So some examples of some physical changes that you can make would be cutting a bar of gold in half, boiling water, or melting a chunk of iron. So if you start off with these materials, for example, with the first example, if you just start off with a bar of gold and you cut it in half, at the end, you'll just have 2 of the bars of gold. It's going to have the same composition. It's going to be the same thing as the gel. Chemical change is changes to the chemical characteristics of a material. So when this happens, a new substance is formed and it will be an irreversible change. So some examples of this would be burning a piece of wood, milk going sour or curdling, and also digesting food. So for example, for the first one, burning a piece of wood, a new substance is formed from the wood. You're going to get ashes, things like that. So that's why we would consider it a chemical change, because ashes do not have the same composition as the original piece of wood. All right. Now we're going to be going over net ionic equations. So net ionic equations are useful to show species that are actively involved in a reaction, and it removes these things called spectator ions. They don't change towards the reaction, and they don't participate in the reaction that's going on. So the first step in determining the net ionic equations would be determine which species are soluble or insoluble. So in the given equation, what do you guys think are the soluble ones? The ones highlighted in yellow or the ones highlighted in white? Right. So the ones that are highlighted in yellow are soluble, they're aqueous solutions, whereas the H2O in this liquid state is insoluble. So next, we are going to verify that the reaction is balanced. In this case, it already is balanced, so there's nothing to worry about. But if it wasn't balanced, then we would have to fix the ratios to make sure that we have a balanced equation. Next, we're going to write the complete ionic equation. So HCl and NaOH, we know dissociates into ions. So we're going to write them as the ions. So we have H plus aqueous plus Cl minus plus Na plus OH minus yields H2O plus Na plus Cl minus. So notice once again, H2O does not dissociate. So we're going to, our next step is omitting spectator ions. So you're going to compare the reactant side of the equation to the product side of the equation. And you're going to notice that Cl minus and Na plus appear as the same thing on the reactant side as well as the product side. So we're going to cross these things out. These are spectator ions. Next, once you cross those out, you're going to write the net ionic equation. So we call it a net ionic equation because, once again, we're only including the things that actually react. So we'll get H plus OH, that should be minus, yields H2O. Okay, so when you are balancing equations, one really important thing to remember is going to be the law of conservation of mass. Mass cannot be created nor destroyed. It doesn't just disappear from your equations. It's going to be present in the same amounts in the reactant side as well as the product side and vice versa. You're going to accurately represent the reactants needed in a reaction. So you're going to have accurate product representation as well. All right, so we're going to go over stoichiometry now. So stoichiometry is used to calculate products through known reactant amounts and vice versa. So if you know how much of a reactant you have, or how much of all reactants you have, you'll know how much products you have, and vice versa. So the core concepts of stoichiometry is going to be balancing equations, making sure that there's an equal number of molecule A on both sides, and as well as molecule B, knowing the molar mass and working with it, how to work with it, and also understanding the relationship between reactants and products. So we have an equation over to the right. Is this equation balanced? Okay, let's take a look at it. So you have one molecule of Al on the left, and on the product's reactant side, sorry, and on the product side, you also have one molecule of Al. So the Al is balanced. For hydrogen, we have 2 moles of hydrogen right as well as 2 on the left. So that's balanced. So for SO4, we're going to have 1 mole of SO4 on the reactants, but it looks like we have 3 moles of SO4 on the product side. So this equation isn't balanced because that one reactant is not balanced on both sides. So we're going to want to balance it by adjusting the ratios of each mole. So how about you guys take a second to balance it on your own, and we can come back and compare our answers after like a minute. All right, we can come back and check our answer now. Okay, so is this what everyone put down? I'm going to end up having this. Sorry, the AL should only be 1 there. And then otherwise, it will be balanced. Yeah, it should be AL2, correct. Okay, so we can move on to the next slide. Okay, so we're going to do a checkpoint, and this is going to be practice with molar masses and how many grams of one substance can be formed, how many grams of a product can be formed, given the amount of a reactant. So the question is asking, how many grams of Cl can be formed from 1.25 moles of AlCl3, according to the following reaction. So key things to point out in this question, I would just go ahead and circle these things in the question itself. So it's asking for the final answer in grams of Cl, which is the product, and we're given a number that is the moles of the reactant. So I would go ahead and note that, as well as check the relationship between how many moles of the product are formed per reactant. So we can see that for Cl, 3 moles of Cl are formed per 1 mole of AlCl3. So how about you guys take a minute or two to try this question out on your own, and we can come back and do the answer together. And as a reminder, so you guys don't have to check your periodic tables, Cl is 35.45 grams per mole. All right, we can go look at the answer and the work for the question. So yeah, make sure you did use stoichiometry. That's what it mentioned earlier with 3 moles of Cl formed per 1 mole of AlCl. So this is how you would set the equation up when you're showing your work. So you're going to have 1.25 moles of AlCl3, which is what was given to us in the question. And we're going to find a way to cancel out the AlCl and end up with moles of chlorine. So we're going to multiply that by 3 moles of Cl over per 1 AlCl3. And it turns out that if we react 1.25 moles of AlCl3, then we will end up with 3.75 moles of chlorine. And once we have that number of moles, we can use the atomic mass, which is really hand grams per mole. So again, we can set up the equations. So we're going to end up canceling out moles of Cl. So 3.75 mol times 35.45 per 1 mole of Cl. And that will give us with 133 grams of Cl. Yes. So we have 3 sig figs there because the 3 sig figs is what the number of sig figs in the question was given. So you generally want to, yeah, a lot of people say you should go by 3. 3 is a really safe number. Usually you want to go by the lowest number of sig figs in any number that's given to you in the question. All right, now we're going to do a review of titrations and what they are. So titration is a method to determine the concentration of an unknown substance, which would be the analyte, by slowly adding a substance of known concentration, and that will be the titrant. So we often do titrations with acids and bases. So usually you'll have a substance that has unknown acidity, and you want to find out what it is by adding a base of a known acidity. Then we have our equivalence point, which is when the titrant just barely neutralizes the analyte. So by neutralizing, that means that the reactant or the analyte will have the same number of moles as the titrant. Next, we're going to have our endpoint. So equivalence point is just when you're actually doing the titration, and there's going to be an indicator, which is our next vocab term, which is a substance that changes color at certain pH levels, and that allows for a visual indicator of the equivalence point and the endpoint. So when you're finding the equivalence point, that's when the substance or the solution, just starts to change color, and the endpoint is when the solution completely changes color. And we have a video to show the lab procedure of the titration. Sometimes you will be questioned about certain lab procedures on the AP exam, so it's really good to know them. So I'll mute up while we watch the video. Okay, guys, 1 second while we figure out how to share the audio. All right, so that was the video on titrations. I don't know why my camera's not working, but I guess we'll go cameraless until that works. So this was a really good video. It explained all the different steps, all the different materials, as well as some of the calculations. So one of the biggest takeaways from this video, I'd say, is one, knowing what the materials for doing titration are. So BRES are always for titration, and also something with knowing what unit to round your milliliters to. So always round to the nearest 100th of a milliliter, because you will get points taken off. You have to guess the 100th milliliter because it's not exactly clear from the burette markings. All right, we can move on to the next. The camera's working now. Just a moment, guys. For the accuracy, I'm not sure how close they do want you to be on to the actual answer that they give. I would assume within 0.05 milliliters, something like that.
One second, you guys. We are getting the slides pulled right back up.
One more second, guys.
Okay, let me. I got y'all. Let's see, right here. Can you guys see this? Oh, is it not screen
yet.
sharing? Yeah, on my end it says it's screen sharing. Let me try again. Hold on.
Oh, no. Guys, the call is
going on stage. Hi, everyone. There we go. Did it work?
Not yet. At least for me.
Oh.
It's showing for me.
Did Kritika just vanish? Anyways, so we got titration curves over here. I guess I'm gonna do a little chatting. But with what you guys saw on the previous screen of the titrations, basically when we have a titration curve, you can do a really lovely graph by graphing all of the small little data points about how much you're adding versus the pH. So what you can see over here is that like when the pH takes a really sharp turn, so for example, like you'll have this one moment where like you add in one more drop and the pH like spikes up super high, or if you're doing the reverse, it might drop down super low. But with that, with that, you can see the equivalence point. When you're doing titration, really easy to go from like the equivalence point to the end point. And then you'll see the equivalence point at that, like, I'm sure you guys know how satisfying it is to see the like really, really pale, like pink. And then if you add one more drop and it turns like super pink, that really, really pale pink is where you want to stop it. And then that's where you have your equivalence point. And then if you end up overshooting it, that is your end point. And then sadly, you've gone a little too much. So here are the different graphs about how it looks like from strong acid to strong base, strong acid to weak base. So these are really like important to know, not necessarily to memorize, but just to know how it would look like. Just because for example, you can be given on the AP exam like a graph of one of these, and then you should be able to figure out like from this it's like, oh, is this like a weak acid or like a strong acid, stuff like that. So we'll just move on. We have a short little break here, but for the time being, I think I will move it to 5 minutes. And I promise you guys, wait, hold on. Let me just like, okay, for 5 minutes. And then I promise you guys, we're gonna have samosa today. And I know you guys love samosa, so we will definitely have that. Okay, I can answer a few questions while I'm up here. Yash, if you want to come on stage, I know you're going to be doing the next section. And I guess while this break is going, if you would, I don't know. Oh my god, I see all the French in the chat. You guys have not lived if you haven't heard samosa. So we will definitely be doing that. I hope you guys have been paying attention because end of Unit 4, we have a small quiz for you guys. So yeah. Yeah, there's a question section in the chat. I think if you like hover over your text, I don't know if that might be just like a host thing, but you can also just like put it in there yourself and pose it as a question. Not sure if that's like just a host thing, but yeah. Okay, I see a few questions about like, okay, yeah, we can go back one slide. There's 3 minutes, but I can talk for a little bit. I can yap. But I see some people were asking about where is it? Like drawing like where the equivalence point is and stuff like that. Okay, so like let's talk about like a weak acid strong base titration. So like within this type of titration, like you have the weak acid titrating the weak acid in like the what do you call it, like the beaker or whatnot, and then you have the strong base within the burette. So you're adding the strong base slowly. So at the equivalence point, so that means all of the weak base has been neutralized by the strong base. So that means the amount of moles of the strong base is the same as like the amount of moles as the strong acid. So like the resulting solution is the conjugate base of the weak acid. And then so the pH should be greater than 7, but it won't reach the pH of the strong bases solution because the conjugate base is won't completely dissociate. So like I don't know how to like specifically tell you an answer to this, but usually it will be between like 8 and 10. I feel like that's like the most like mostly what I see in the lab, I should say. And then for like the opposite, when you have a weak base and then a strong acid titration, that usually will be around like 4 and 6. Usually you see like strong acids like 3 and below, and then like 4 and below, 3 below, but then for strong base you see it like 10 or 11, and then more than that. So I hope that helps. Okay, so I've yapped enough. I will leave it to you guys. I believe Yash is taking over. Um, we did our little break already. So, Yash, would you like to screen share? Is that cool with you?
Yeah, I can for sure.
No, no worries. Anyways, I will be leaving now, guys. Thank you for having me on stage.
All right. Hey everyone. My name is Yash. I'm a junior in high school. I'll be taking over for a little bit. So just waiting to screen share. Can you guys see it? Yep. Okay. So again, we're just gonna be looking at the types of chemical reactions. So these are two more types: acid, base, and precipitation. So for acid base, it's pretty simple. It's just a transfer of a proton. Again, if you want to do a quick review, the Bronsted-Lowry definition for what an acid is and what a base is that an acid donates a proton. So something like HCl, H3O plus, H3PO4, those all donate a proton. And a base is something that accepts a proton. Um, Examples of common bases are OH minus, NH3, OCl minus. There's some common bases you might see. And remember, a proton is just the same thing as an H plus ion, because a proton is literally just one proton, which is the same thing as a hydrogen atom without its electron, which is the same thing as just the H plus. So quick exercise for everyone in the chat. Let's go ahead and identify the acid and the base on the reactant side of this equation. So just write your answer. Acid is whatever, base is whatever. Amanda, yes, you probably will at some point in the exam. We'll look over it later. Next night or next night when we go over the acid base unit. Yep, you guys are right. The acid on this side of the equation is HCl and the base is H2O plus. It's not listed here, but there are charges. This is hydronium H3O plus, and this is chloride Cl minus. Yep, that's right, guys. All right, so a precipitation reaction is just a reaction of a cation and an anion, resulting in the formation of a precipitate. So a precipitate is just a soluble substance, or an insoluble substance. So for example, if you have silver nitrate plus sodium chloride, the Ag plus and Cl minus come together to form in the insoluble silver chloride. Another example is cadmium sulfate plus potassium sulfide. The cadmium 2 plus comes together with the S2 minus to form cadmium sulfide CDS, which is also very insoluble in water. Yeah. Remember that in AP, they really won't test you too much about solubility rules. All you'll need to know is that most nitrates and group 1 salts and ammonium salts are all soluble. They'll usually give you KSP data or they'll tell you what salt is insoluble. just a common thing you might want to know is that Ag plus precipitates Cl minus, Br minus, I minus. It's a very common FRQ question they have, which might be helpful. Next slide, please. All right, so here are two more types, or here's another type of chemical reaction. It's a redox reaction. So redox really just refers to the transfer of electrons. Redox is really just the transfer of electrons. So we know that oxidation is when a substance loses electrons or it gains charge. The charge goes up. And a reduction is when a substance loses charge or gains electrons. So a really helpful way to remember the difference between oxidation and reduction is oil rig. I'll put in the chat oil rig. So oil oxidation is loss. Oxidation is loss of electrons. And reduction is gain. Reduction is gain of electrons. All right, so it's a little confusing, and so we'll work through it for a step-by-step for this problem. So here an example of 2Mg plus O2 gives you 2MgO. In the chat, can you guys identify what type of reaction this is from our 5 types before? Our synthesis, decomposition, double replacement, single replacement, combustion. So you're right, it is synthesis. Good job, guys. All right, so if we look at the oxidation states on the reactant side of the equation, we have just pure Mg metal. So that is an oxidation state of 0. And we have pure oxygen gas. So oxygen has an oxidation state of 0 too. On the product side, we see that we have the ionic compound MgO, where magnesium has its characteristic 2+ charge and oxygen has a 2- charge. So from this, we see that since the Mg gained charge, it must have lost electrons, or it must have been reduced, or it must have been oxidized, sorry. So, must have been oxidized. Similarly, the oxygen decreased its charge, or it gained electrons, which means it must have been what, guys? Oxidized or reduced? Oxygen was oxidized or was it reduced? Reduced. Yes, that is correct, guys. Oxygen was reduced. All right, so here's a limiting reagent problem as a checkpoint. So this question asks us to identify the limiting reagent in this reaction. The reaction is 2H2 plus O2 gives you 2H2O. We start with 4 moles of H2 and 4 moles of O2. So how do we find the limiting reactant? Anyone in chat want to answer it? H2 is the limiting reactant. That's right. All right. So for this problem, you really just want to use stoichiometry. Using stoichiometry, we start with 4 mole H2. We know that for every 2 moles of H2, we'll get 2 moles of H2O. So for 4 moles of H2, we'll get 4 moles of H2O. Similarly, for 4 moles of O2, we know that for every 1 mole of O2, we'll get 2 moles of H2O. So for 4 moles of O2, we'll get 8 moles of H2O. So looking at comparing our 4 mole H2O and our 8 mole H2O, we see that hydrogen gives us less H2O, so hydrogen is our limiting reactant. Yes, Vivian is correct. All right, so here's some conceptual questions. What is the significance of the equivalence point in a titration? And explain how to determine whether a salt will produce an acidic or basic solution. when dissolved in water. So let's take this question by question. Just answer question 2 in chat, guys. So you guys are on the right track. The equivalence point, yes, Jonathan, that's exactly right. Where is the equivalent? The equivalence point is where the titrant has completely reacted with the analyte. If you have an acid-base titration, it's when the acid and base have perfectly neutralized each other. It's not necessarily where the pH has to equal 7, as we'll see later on during the Cram sessions. The pH will only equal roughly 7, in the range of 7. If you have a strong base, strong acid titration. We'll learn later. So user 3 dBA, when you say acid equals base at half equivalence, the concentration of the acid equals the concentration of the conjugate base at half equivalence. We'll explain that in much more detail tomorrow. But at the equivalence point of titration, it's just the point where the entire analyte has been reacted with by the titrant. Yes, Kendall, salt can produce either a basic or an acidic solution in water, depending on what salt it is. So, looking at question number 3 now. A salt can produce an acidic or a basic solution depending on what kind of salt it is. So say you have a salt like NH4Cl, ammonium chloride. So ammonium is a weak acid, NH4 plus. It's the conjugate acid of NH3. But Cl is a basically doesn't do anything because it's the conjugate base of a super strong acid, HCl. So Cl is basically neutral. So NH4 plus acts as a weak acid and makes the solution acidic. And so in that way, your salt is acidic. Conversely, you could have a solution of NaF, sodium fluoride, where sodium, again, is neutral and doesn't do anything, but F minus is weakly basic. So your solution will be basic in that case. If both ions from your salt are neither weak acids nor weak bases, your solution will remain neutral. An example of that is NaCl, where neither one of them will react. All right, let's do this MCQ practice. So this is a 2-minute question. A chemistry teacher carried out several demonstrations and students recorded their observations. For one of the demonstrations, a student concluded that a physical change took place, but not a chemical change. Which of the following observations could the student have made of the results of the demonstration? So yeah, go ahead and answer that. Please refrain from putting your answer in chat until you have until the timer is up. Okay, guys, I just said don't put the answer in chat, but I love your enthusiasm. I love your enthusiasm, guys. It's great. You guys are gonna do great in the exam, but just for now, let's not do that. But it's fine. At this point, I think you guys all got it. It is C. So great work on that. So remember that a change in phase, size, or shape, that's all physical changes. So if you just cut up the thing in small pieces, the substance identity does not change, and therefore is a physical change. Yeah. I seem to have gotten that down pretty well. Okay. All right, so we do have a practice quiz. Yeah, scan the QR code to join. And if the QR code does not work, I can put a link in the chat. But I think I will just do this. Just to confirm, change in color is always a chemical change. Yes, almost always. I can't think of any exceptions off the top of my head at the moment.
Is samosa working?
I don't know. There are cases where the color can change and it can be a physical change, but I just can't give you an example at the moment. I can't think of anything. I don't know if the music is working on Nova. Can anyone
Do you
hear
want me
it?
to try screen sharing?
Yeah, that's cool too.
Okay. Give me a sec. I'll let you guys still stick with it, but
I think they can hear it on their side too, right? If I'm not mistaken.
I don't think so. Wait, can you guys hear me? Oh, okay. Here, I'll screen share. Let me know if you guys can hear it.
Okay.
Let's go.
Yeah, that is right. Painting a canvas or dyeing something is a physical change with a change in color. That's a good example.
Is this a good volume, or
Yeah,
should I make it a little quieter?
a little quieter, please. But
No worries.
yeah,
Is that okay?
yeah, that's good. All right.
Oh, I guess we're already starting.
I can control it. It's just if you play the music,
Okay.
you don't have to worry about controlling. Yeah. Yep, you guys seem to have done pretty well with this. So a redox reaction again is when oxidation states change, and that just means that some atoms gain electrons, some atoms lose electrons. A boiling of water is a physical change, so you can rule that out almost immediately because the redox reaction is a chemical reaction. Dissolving sugar in water is again just a dissolution. No atoms are being chemically changed, so you can rule that one out. There is in corrosion of metals, for example, an example of a reaction that expresses corrosion of iron, for example, is iron, like Fe plus O2 oxygen, goes to Fe2O3, rust. Can you not hear me? Okay. I think we can have the volume a little bit, maybe just a little bit lower.
I just muted it.
Okay.
So yeah, I'll turn it back on once you finish talking, and then I'll only play it when people are answering the question.
Yeah. Okay, so as you know, the iron is going from 0 to +2 or 3, and that means that its oxidation state is changing, making this a redox reaction. Conversely, the oxygen also goes from 0 to -2. For D, it's another physical change. That's a change in the phase of the substance from liquid to solid. So that is not a reaction, not a chemical reaction. So it cannot be a redox reaction. All right. All right, so this problem was a little bit more difficult for us. That makes sense because we haven't really talked about Le Chat. But basically, Le Chat is when you remove substance from equilibrium, the equilibrium shifts to minimize the change that you made. Let's not talk about this question in too much detail right now. We'll talk about Le Chat in great detail tomorrow. So if you are confused about this, Le Chat is not really in Unit 5. Unit 5 is more about different types of reactions, so Unit 4 is more about different types of reactions. So yeah, Le Chat is one of the later units. Well, if you are confused with this question, we will explain Le Chat and equilibrium in a broader context later.
I'm sorry, guys. I don't know why. What do you call it? Samosa's not working. It's not even playing on my end. I'm sorry, guys. Okay, guys, fingers crossed. I'm gonna just refresh my page. Let's hope it didn't ruin anything. Okay. Okay. Samosa's no longer shy, guys.
Alright. Seems like you guys did pretty good on this one. Again, alkaline metals will typically form those +1 cations, as you can see that they're on the farthest left off the periodic table. So if they lose one electron, they'll get a noble gas configuration from the previous period. So they'll typically lose one electron. Isabella, for memorizing the solubility rules, don't worry about it too much. It really won't be tested in too great detail. Alright. Seems like this question did provide a little bit more difficulty for us. So in this reaction, calcium carbonate precipitates out as it is insoluble. Most carbonate salts that are not group 1 salts are actually insoluble. Calcium carbonate, strontium carbonate, iron carbonate, zinc carbonate, etc., etc. So the sodium does not react, the chloride does not react, and therefore those two are the spectator ions. B and D are wrong because the carbonate reacts to form a precipitate, calcium carbonate. C is wrong because the calcium reacts to form the precipitate, calcium carbonate. Is there any questions for this? This is a question I feel like they could definitely ask on the AP exam, pretty much word for word, bar for bar. Okay, I think we're good. Vowel for vowel, yeah. No problem, knocked out. Are these certain things always good solved? Certain anions will tend to precipitate more frequently, but everything has its exceptions with solubility. They'll usually give you KSP values, so don't worry too much. So I actually believe this question might be incorrect, and I think the correct answer is actually 11 liters of carbon dioxide, as I believe the reaction equation would be 2 sodium bicarbonate to 1 sodium carbonate and 1 carbon dioxide gas and 1 water. So I'm not sure. Let's just pretend that the question didn't exist, and let's move on. If anyone wants me to explain why it's 11 and not 22.4, I can go ahead and do that by writing out in chat the explanation. If it's 11, I would cover. Yeah, sorry. It does not produce carbon dioxide. Carbon dioxide is not as thermodynamically stable as carbon dioxide, so it does. Yeah, okay, I can write it in chat. So sodium bicarbonate, obviously NaHCO3. Let's all stop typing for a second so I can write it out. So this is the reaction equation. You can see that for every 2 moles of NaHCO3, you'll get 1 mole of CO2. So in the problem, there is only 1 mole of NaHCO3, so you'll only get 0.5 moles of carbon dioxide. And you just do 0.5 times 22.4 liters, as there are 22.4 liters of gas in 1 mole at STP at ideal conditions, if we assume everything to be ideal. So yeah, the answer to this question should be 11. Do you guys see the logic behind that? Anyone want a second explanation? Yeah, this is a common trick. Just write out the equation as much as you can. So once you have 0.5 moles of carbon dioxide, you know that carbon dioxide is a gas, right? And at STP, this is on your reference sheet, I believe, but at STP, there are 22.4 liters of gas, approximately, in 1 mole of gas. So you can just do 0.5 mole times 22.4 divided by 1 mole, and that gets you around 11. You can use the ideal gas law, PV equals nRT in the situation, but since you have this conversion factor, 22.4 liters in 1 mole of gas at STP, I would recommend doing that. Jasmine, does that answer your question? All right, cool. Yep, you guys seem to have done really good in this question. This is the definition question. Empirical formula is just the simplest whole number ratio of elements, and molecular formula is the exact number of atoms in each element. So yeah, great job on this question, guys. Let's skip this question. And this question too. This is a Unit 9 question, I believe. Alright, let's do this question. Yep, you guys seem to have got this question pretty well. Again, the phenolphthalein indicator is just there for you to be able to visually see the endpoint with the shifting color. Yep, that's pretty much it. So I think we'll be passing it over to Rahi, and Rahi will be doing the next set of slides. So thanks for having me. I'll be back for the next quiz.
All right. Let's get me resharing. You guys will have like a break, so don't worry too much. I'll give you a break. There we go. Okay. Okay, you guys will get a break. Yeah, I'll keep it at 10 minutes. So I will see you guys at 7:28 Central. I'm Central. 8:18 Eastern. 5:18 Western. Bye, go get a drink, get some water. I'm gonna stop talking. Oh. Wait, do you guys want me to yap? I'm gonna yap. I got you. Okay, the street sign. I do have a street sign behind me. It's right there. It's electric. What is it? It's an electric vehicle charging sign. I didn't steal it. Okay, I'm not doing like bad things. For reference, I didn't steal it. It was given to me by my neighbor who like he like works on this stuff. Like he like, you know, you guys can hear me, right? Muted? I don't think so. Okay, we're good. Yeah, my neighbor gave it to me. I don't know. Okay, yeah, maybe Haley. I don't know. Maybe he stole it. I don't know. But like, it's not my problem. But he gave it to me, and I was like, yeah, I'll put it up. The license plate is an old license plate. It's like an old license plate from one of like a car that I used to have that I don't any longer. So that's why that's on my wall. But if anyone knows how to get more street signs, let me know. Yeah, anyway, AP Chem. A couple tips for the exam. If you guys are still want me to talk, I will. A couple tips for the exam is I write everything out. I don't particularly care if it's like, you know, it's one of those questions that you just like feel like, you know, it's like, you know, I do write everything out, regardless of the fact. I like, you know, equations, I write them out. Balance stuff. Yeah, please keep the chat legal, please. Okay. But yeah, I like balancing stuff. You know, I write everything out. I don't try to do a lot in my head just because like you do make a lot of mistakes. So, you know, try to do that. Also pace yourself. Going too fast is actually, I think for me, like I will say like it's like a little bit different. For like everyone. And I know some people like struggle with like keeping on time, but for me, like the tempo specifically for the AP exams, I feel like they're relatively lenient on time. I don't know if you guys do, but I tend to go fast. So I almost like divide the exam up. And I'm like, okay, if I have, I don't know, 2 hours for like this particular section of the exam, at an hour, I want to be halfway done. And I don't really want to be 3/4 or like 7/8, 5/6. I don't want to be too much more than halfway done. because like it does get to be a problem when you guys are like, when you feel like you like are going well. I mean, I pray that you guys look at each question, you're like, oh my God, I know this. Oh my God, I know this. Oh my God, I know this. But if you get into a rhythm of doing that, sometimes you might feel like, oh my God, I know this, when you don't, oh my God, I know this. And then we don't want that. We don't want that, right? So actually, related point to ANOVA, I didn't do that on Chem, but I did that on, what did I do that on? I did that on my A push. I did it on one of my A push DBQs. I literally, like, you know how you have to contextualize? I literally wrote, like, I don't know the context for this. And I got a 5. So it is what it is. Yeah. I am like reading the chat. I am reading the chat. So if you guys do have like general questions, I mean, if you want like questions about AP exams in general, AP testing process, that's cool. I'm not gonna like talk about other classes, but like, you know, ask away. College, I guess. You guys have any college problems? You guys are thinking about college, right? I'm in college. I'm not in college. You wanna know why? I graduated yesterday. That's why. So that was that. I went past tense to Nova Southeastern. I graduated in 3 years there. I got my BS, about my bachelor's in biology. I got a minor in psychology. I got a minor in business. I got a minor in pre-medical. And I'm going to med school next year. So I know. So that was cool. I'm okay. Fake stuff is crazy. Fake stuff is crazy talk. But yeah, so that's what I did after college, or after high school rather. So, oh my God, wait, what? Are any of you guys or seniors? What colleges are you guys committing? You guys should be committing, right? What colleges are you guys committing to? Talk to me. What's going on? Northwestern, congrats. That's amazing. I live by Northwestern right now because I came back home. I live in Chicago, or well, in the Chicago suburbs. So I'm close to Northwestern. UConn, UCSD. Okay, both amazing choices. I got into UConn. Didn't apply to UCSD. I didn't apply to the UCs because of that like external application. That UC application really made me upset. I can't lie. McGill, Canada? Okay. I know someone that went to McGill. They loved it there. It's cool. Cornell, congratulations. Vanderbilt, VCU, okay. Oh my God, yeah. Anuva and Elias are both like the small liberal arts college people, which is really funny. Because like they're really like they're going to amazing schools, and I'm sure they're amazingly very smart individuals, and I love them both. But it's funny because you say it, and the people don't go, "Oh my gosh, wow!" But they go, "Huh?" You know, like that's their first reaction. Okay, like it's amazing. Don't get me wrong, but that is their first reaction. What year did I take my MCAT? I took my MCAT end of sophomore year, so end of my second year, right? So literally a year and 1 month ago, I took it in April 14th. I remember the day because it's ingrained in my memory. Because why wouldn't it be? I only had to take it once, thank God. I prepped. I look like I went to Niles West. No, I went to Conant. That's my high school. If you guys know where that is. If any of you guys are in Chicagoland, it's a pretty big school. So, the recordings for yesterday in your My Stuff section of the 5 Bowl. I would look there. What did I get on the MCAT? I got a 520. Fired on the spot. It's crazy. $520 out of 528. Okay, listen. I know people say about ANOVA. I know. But I will say that if you guys are looking into medicine, it's a direct admission program into like a 7 or 8 year medical program. That's like where you do your bachelor's and then hop straight into like your medical school. So if you are doing like a lot of pre-med stuff and you have like friends or something that are looking into that world specifically, a lot of them do know what NOVA is. So I will defend myself a little bit there. Okay, Rahi cheated is crazy. Rahi did not cheat. I'll have you know. Rahi is an honorable individual. And Rahi needs to stop talking in third person, actually. The neighborhood, the street signs. Wait, did I not say where? Oh, I go to I'm also going to Nova for med school. I'm also going to Nova for med school because I'm in the program. So yeah, why are we blaming Rahi? Although you guys are asking me. Oh yeah, okay, yeah, I wasn't supposed to be on tonight. But I will be. If you guys are there for the first preview, that's where you guys saw me, and then I kind of disappeared for a little while. But I was here yesterday. Do I have any cars tips? Okay, you want to know my cars tips? Is if you're here at an AP Cram session, you're in high school, and please, for the love of God, stop worrying about the MCAT. Please. That is not in your near future. Okay? Please. Live life, guys. Live life. Live life. Okay? There's more than worrying about the next standardized test. I promise. I promise. All right. That's my answer. Yeah, but I did take over. I am taking over current tense for Kritika. So yeah. All right. Well, our time is up to yap. Although I think we have another break, so maybe I'll yap more. You guys will get more of me. I promise. You guys will get more yapping. If you guys want more yapping, I'll give you. You know, I'm a man of the people. I love you guys too. All right, let's talk about kinetics. Kinetics is a big unit, okay? It's unit 5. It's 12 to 17% of the exam. So yeah, I would say we're going to go over most of the stuff. Do be warned, it's a big unit, not just on the exam, but it's also a big unit in quantity. So we aren't going to cover like every little bit, but we're going to hit the main points for sure, I promise. So yeah. All right, let's take a look at the topics. The topics are intro to rate laws, concentration changes over time, elementary reactions, collision models, reaction energy profile, intro to reaction mechanisms, reaction rate and I saw Elias say Riz. I read Riz. Okay. Reaction mechanism and rate law, steady state approximation, and catalysis. Okay. So let's talk about reaction rates, right? Reaction rates are the rate at which a reactant is converted to products per unit of time. It's pretty self-explanatory. Reaction rate is literally the rate of the reaction, like of that particular chemical reaction. And they're we determine them practically by looking at reaction mechanisms and by testing steps of reaction mechanisms. And that's what we're going to talk about today. Kinetics overall, this topic is about the studies of reaction rates and how reactions proceed, which is broken down into reaction rates and reaction mechanisms, okay? And reaction mechanisms are molecular events that control the speed, which is the rate, and the outcome of a particular reaction, okay? So let's look at some important terms to know. Some important terms would be the initial rate. What does that mean? It means what is the current rate of the reaction at t equals 0. Someone said I'm frozen. I'm going to keep talking, but tell me if I am frozen and I'll stop, okay? The average rate is the rate of the change of concentration over the course of the entire reaction. Well, when you do an average, what do, right? You take something and divide it by however many you got. In this case, we take every particular concentration we have, which is the change in concentration. We do that by taking the final minus the initial concentration, and we divide it by the amount of time that the reaction has occurred for. It's literally the same as an average. I mean, I guess in math, but also particularly in average in physics, they use it a lot. So if you guys are taking physics, I'm sorry, but instantaneous rate is the rate at a specific time. Essentially, an instantaneous rate is literally like a snapshot, right? We're like taking a picture of the current state of a reaction and seeing exactly what's going on there. What rates on the reaction are occurring at this particular time. Initial rate is technically an instantaneous rate, but initial rate is the particular instantaneous rate at specifically t equals 0. Okay? And here's a nice little graph. So the initial rate would be at the very beginning of the x-axis where time is 0. The average rate would be the change in concentration over the time. So we took the change in the overall change in concentration from the beginning to the end, and then we divided by how long the reaction actually occurred for. And the instantaneous rate is the rate at any specific time that we can look at. All right. Okay. So that was weird. So reaction rates are dependent on certain things. Reaction of a rate does not have to be constant because changes in the system can occur. And that's a really big thing. So, I'm sorry. So that's really important to recognize, right? We talk a lot about, when we talk about like gas laws and when we talk about stuff like that, it's kind of similar in a way to Le Chatelier's and stuff like that we'll talk about in another unit. But yeah, so reaction rates can change dependent on the rate and product concentration. I think this one's the most self-explanatory one, because what happens if you have a higher concentration of a certain reactant? Well, there's more chemical interactions between the molecules of that because there's literally a higher proportion of those in the solution that you have, right? And that means that you're going to get a faster reaction. That's pretty logical. Temperature is along a similar vein. We have to boil it down to like what makes a reaction occur, right? Reactions don't occur when like two things just appear and then boom, they've reacted. It might seem that way to us because we're big bumbling creatures with not eyes that can see molecules. But reactions specifically occur within chance interactions. So without getting too deep into it, it's when molecules hit each other in a certain way that makes them react, that makes that chemical interaction change such that we can say that for us, that reaction has occurred. So for temperature, what happens? What is temperature? Temperature is a measure of how much kinetic energy a given molecule in a solution has, right? So when you have a higher temperature, you practically have a higher rate of kinetic energy. And that means there's more movement and more collisions, which means there's a faster reaction. Someone said we'll go back to the last slide. I do have to keep moving, but you do have access to the slide, so you can always look at it yourself, okay? Surface area is kind of a similar thing. It means that if there's more exposed area, what does that mean, right? If there's more exposed area, that means molecules can interact more. Because like in a solid, the molecules in the middle of a solid, if you think about like a solid, the molecules in the middle of a solid don't experience the same like interactions to something else as the molecules on the surface of a solid. So what happens when you have like stuff like powder? Well, powder has a lot of very fine particles, which means that all of those particles are particularly exposed, right? And that means you'll have a faster reaction. And catalysts, we're going to talk about catalysis specifically, but catalysts lower the activation energy and their faster reaction. The one thing I will tout always, is that catalysts are not used up in a reaction, ever. Catalysts are always refreshable, okay? And they lower the activation energy. We'll talk about catalysts, but they don't change the overall energy of a reaction. They lower particularly the activation energy. That one's really important. I'll say it probably 5,000 times, and you'll probably want to slap me across the face for saying it. But I gotta. Okay. So let's talk about rate laws. Rate laws. The standard rate of reaction is K, which is the reaction constant, rate constant, and then the concentration of 1A to the end and the concentration of B to the N, right? Does anyone know what the N represents here? I know it's an exponent, but like what does it represent? Like what practical numbers would we be putting in there? Think about that for a second. Yeah, there you go. Excuse me. Thank you. Yes. It would be the coefficient, right? But now I'm going to ask you this, okay? I'm going to answer this. This is a little bit more rhetorical, but why is it the coefficient? Why does that make sense? Okay, because I encourage you to think about why, and I always will, because a lot of the times it is important to A, understand the why because you'll remember it more, but also understand the why because AP can ask you things that they expect you to derive. It's not necessarily something that you would have been taught, but based on the information that you generally know, you should be able to draw conclusions. Right? So why is it the coefficient? Why would we do A to the first if it's just A? And why would we do B to the second if it's 2B? Okay? And the answer here is because we're talking about interactions, right? We're talking about how much of any one given thing is required for a reaction to proceed. And what does that mean if you need two? There, exactly. There you go. Good job, Tessa. Because the concentration is exponentially increased as per the moles increase, which means that you experience a greater rate of interactions dependent on the amount of, sorry, I'll say that the other way around. The concentration is dependent on how many of these molecules will interact in a particular manner in order for the reaction to proceed, okay? So K is our rate constant, and N is our order of the reaction, and that's why we use our coefficient as N, okay? So let's look over here. We can look at some examples. Our rate law for 2 H2O2 are required for 2 H2O, or to make 2 H2O and 1 O2. And so that means our rate law will be, remember, we only deal with the reactant side of it because we don't really care what products it makes for the rate. We only care about the, the things that we actually need for it. So K, a given rate constant, and the amount of, the gas or whatever we're dealing with, liquid, I guess, in this situation, to the reaction, to the order of how much there is. In this case, it's 2. So that's why it's K, H2O, the concentration of H2O2, squared. Okay? Got it good? Oh. Okay. Okay. That was really weird. Okay. So let's talk about concentrations. Concentration changes over time. The overall reactant order is actually a sum of the reactant orders, right? So 0 order reactions. I saw someone up there, someone say the order is typically either 0, 1, or 2. The order can be more. That's not a hard limit, but we don't see more because it's very, very, very incredibly inconvenient to calculate, and they don't expect you to do anything like that because you get into like some like hoodoo voodoo stuff. Okay, so the 0 order reaction, the units of K in this case are moles over seconds, molarity over seconds, excuse me. There's no correlation between the concentration and the rate of the reaction, and that's why the rate is K, A to the 0. What's A to the 0? Doesn't matter what A is, right? It's going to be 1. So that means the rate is equal to K. So the rate is the rate constant in this case. And that's why our units is the molarity over seconds. Okay. We also have, in this case, this is the concentration of A versus time. Okay. We also have first order reactions. In this case, the units of K will be 1 over seconds, or seconds to the negative first, depending on how you want to write it. The units of the reaction rate in this case will be moles over, will be moles, molarity over second. I keep saying moles, I'm sorry. And then in this case, that means the rate will be K times the concentration of the reactants to the first power, or just K times the concentration of the reactants. Okay. And what does this mean? That means graphically, it will be graphed as the natural log of A versus time. And then second order reactions in units of K are going to be 1 over molarity seconds. And the units of the reaction rates are going to be molarity over seconds. And then the rate is going to be K, A squared, or it can also be K times the concentration of A times the concentration of B. That actually depends on like what any given like particular reaction is. If it's like the one that we looked at before, where it's like 2 H2O2 turns into something, or whether it's like 1, I don't know, can't think of an example off the top of my head, I'm sorry. But like, one thing like plus another thing, and they both have a coefficient of 1. Okay, and then graphically, we would represent this as 1 over the concentration of A versus T. Okay. All right. So integrated rate laws, I'm going to throw them all up on screen, actually, because I think it'll be easier to talk about, because I want you to look at the difference, not just in the shape of the graph, but also like the units. These aren't included in the equation sheet that they give you for AP Chem. So you don't need to like know them off the top of your head because you can just look at the units. However, it's pretty good to understand how to apply them because they do understand, or they do ask questions pretty often, I would say, in like an applicable way when you want to understand like not just what you're looking at, but like why you're looking at what you're looking at. You know what I mean? So in a 0 order reaction, like you said, or like I said, it's a concentration of A versus time. And that means this representation will be the concentration of A sub T, which is the concentration of A at any given time, is equal to negative KT plus A sub 0. And that is the concentration of A at initial time. That like subscript just represents the time that we're talking about. We're trying to find a time, like the concentration of a particular reaction at the time. Then, yeah. Okay. So the reason these lines aren't curved, I do like that you brought that up. The reason these lines are not curved is I want you to look at the units of the graph, right? If we graph this typically as time over concentration, just like we did the 0th order reaction, and we do that for the first order and the second order, then it would be curved. It'll look really weird, right? But the reason we don't do that is because the graphical representation of the first order and second order reactions are different. It's actually for the first order, it's a natural log of A, and for the second order, it's 1 over the concentration of A. The derivations of this are like relatively complicated, so we aren't going to go over them, and nor would I say you need to know them. If you do, that's lovely. Glad your teacher taught it to you, I guess. That's good to know. But you don't need to know them for AP. You don't need to know the derivations of why it's a natural log, or 1 over the concentration. However, you do need to know that it exists, and it will be given to you in your equation sheet. Okay? All right. Oh yeah, and in this case, slope is k. That's what we're trying to do. The reason it's okay. The reason it's a straight line in this case is because the slope matters, and the slope is our rate constant, and that's what we need to know. And that's why our graphical representations are what they are. However, we don't need to know why, like, you know, the mathematical derivation of this is what I mean. Okay, so let's jump to half-life for a bit. Might seem a little bit unrelated, but I promise it's not, because it's in a similar vein. So half-life, literally in the name, it's a time required for a concentration of a substance to be halved. And this occurs practically in terms of questions a lot when they're talking about radioactive substances. Why? Because radioactive substances have a half-life. Okay? And almost all radioactive substances have a half-life. So basically what's going on here is that, like, you know, a substance that can decay and or react, there's two different things, right? A substance can decay. If we're talking about radioactive stuff, it's usually radioactive decay, which means, you know, alpha particles, gamma particles, beta particles, if you've ever heard of those. If you haven't, like, you know, you will, I promise. But yeah, so half-life is not only dependent on, and not only important, sorry, in radioactive decay. However, it's also important in reactions. Why? Because substances react. However, I encourage you to think about this. Okay? When a substance reacts, the reactant, you know, disappears, right? Because it becomes reactant in something else. What happens to the concentration of the reactant? It decreases, right? It decreases by the amount of how much reactant reacted in that particular moment in time, which means as a reactant progresses, the concentration is dropping, right? However, right, is it dropping constantly? No. Why? Because interactions. We talked about interactions before. Interactions will slow down as there's less reactants in solution and more, say you have a liquid solution, more products in solution. If this is a non-reversible reaction, the interactions between the reactants that you want for a reaction to progress will slow down. How much? Proportionally. And that's why a half-life is important. That's what this half-life can represent, okay? So again, because of how reactions work and because of how rate laws work, all of this half-life stuff mathematically is dependent on the rate of the order of the reaction, right? So there's a lot of math going on here. Again, equation sheets exist, so don't freak out about the numbers, please. So mathematically, really quick, I'll look at the half-life of a given substance in a zeroth order reaction is equivalent to the rate of the concentration initially over 2 times the rate of the constant, which means A, brackets A, over 2K. In the first order, it's 0.693. Again, why? Because it's the natural log. It's a natural log derivation. It's not E. That's 2.712 or something like that. But yeah, it's a natural log derivation over K. And then in the second order, it's 1 over K times the concentration of like the given A initially. Okay? But understand more than the equations, understand why a half-life exists, because I feel like that's really important to know. And they do ask conceptual questions. And I know, like, a lot of times, like I've heard, like, people say, not you guys, because you guys are, like, nice, but I've heard people say, like, you know, you harp a lot about, like, the why and the meaning and stuff like that. But I do promise you that these things are important, and people miss because people try to focus so much on the math of chemistry that they miss the why of chemistry, and then they ask you why of chemistry, and then you don't understand. Yeah, the K is the rate constant, okay? Okay, elementary reactions, essentially, again, like the name says, are reactions boiled down to their very simplest form. And in a particular reaction, the interactions, the sequence of interactions is extremely complicated. It's pretty complicated. And it usually occurs to, like, a number of different steps, right? We'll talk about rate-dependent steps in literally, like, a couple slides, actually. But so in a particular reaction mechanism, I thought I heard someone say, I don't know if it got answered, but I thought I heard someone say before, or saw someone say, that reaction, like, why, like, what is a reaction mechanism? And a reaction mechanism, I'll go over it now, is the steps required for an overall reaction to occur. Mechanism is actually just what goes on inside, right? So elementary reactions help us understand that. Okay, reactions involve a sequence of steps. We call them elementary steps. Why? Because they're elementary. They're boiled down. They're simple, simplistic. And it depends on a lot of things. One of the things that it depends on is the molecularity. The Okay, my bad. The molecularity is the number of reactant molecules in the reaction. And the rate law of elementary reactions can be inferred from Stoich. Okay, so let's go over a couple of the elementary reactions. I'll talk about them. Unimolecular reaction is we see it in like things like decay and like some other things, is when one thing, an A in this case, turns to a P, a product, right? Only one thing happens. That one A, not multiple A's, that one A turns into a product that we're given P, okay? Not two A's, because that makes it bimolecular. So let's talk about bimolecular. Bimolecular is when two molecules are interacting and it makes a product, okay? Trimolecular or termomolecular is the same thing, just more. Trimolecular is 3 specifically, you know, A plus 2B equals 1 product C. And simultaneous collision of 3 or more particles is rare because there's not enough physical space. It happens very, very, very rarely, like XF5, like some XEF5 and so like some other molecules, but it's so incredibly rare for collision of 3 or more particles to occur because the chances of more, it's not that the reactions don't exist, but it's that the chances of like more, like 4, even 5 molecules colliding in the exact perfect way in order to cause a reaction to occur is mathematically very close to impossible. So we don't see that. Okay. I know you're tired. I know I've yapped, but instead of my brain, it's time to use yours. Okay? So let's do a checkpoint. My God, look at that segue. I'm insane. Okay, so first, how does changing the concentration of reactants affect the rate of chemical reaction according to its rate law? Think about that for a second. Throw your answers in the chat. I want to see what you have to say, and then I'm going to give you what I have to say. Okay? Give you guys a moment. There we go. Okay. So I'm seeing some good answers. I'm seeing some good ideas. Increasing concentration does increase the rate. Decreasing the concentrations does decrease the rate. These are both true. Exactly, right? Overall, to like kind of condense what you're saying, right, is the concentration of the reactants changes or affects the rate of a chemical reaction proportionally, right? If one increases directly, rather, not proportionally, directly. If one increases, the other increases. Now, by how much, that depends on the order, right? I heard some people say that the order needs to be like, you know, accounted for, and it does. You're right. Right? It depends on the order. We can't just like change one thing and expect it to the reactant or the rate to change the exact same. However, depending on the order, it changes proportionally. However, what happens in a 0th order reaction? What if I change the concentration of the reactant in a 0th order reaction? What would happen to its rate? Exactly. There's no effect. Nothing happens. Okay? That's why the order matters, because in a first order and a second order, it does happen, right? Something happens. Now, about how much, it depends on which one you're talking about. However, in a 0th order reaction, nothing happens. The rate of the concentration of the reactants is not dependent on the rate of the reaction. Second checkpoint. What factors determine the rate law of a reaction? We just talked about this. There's 4 main factors that I'd like you guys to focus on for the AP exam. Give me, everyone like, okay, don't try to type out all 4. How about this? Everyone give me one. Give me one. And hope we got all 4. I'm seeing concentration. Yes. I'm seeing temperature. Yes. I'm seeing catalysts. Yes. I'm missing surface area. Thank you. Surface area. Exactly. talked about that. I'm not going to go over like, everything again because you guys are getting it. But remember why everything occurs, not just what. I don't want you to remember an arbitrary list of 4 items. I want you to remember why those 4 items occur. Okay? Yeah, stoichiometric ratio is generally just concentration. Okay? All right. Ooh, 1 second. There we go. Okay. So the collision model is described by the Maxwell-Boltzmann distribution curve. And what that means is like the whole thing that I was just yapping about, how I was like, oh my gosh, like collisions all matter so much, right? And not every molecule will always react when it collides. That's dependent on this Maxwell-Boltzmann curve. So I talked about it in a very like, not fully understanding way because you guys don't need to understand it comprehensively. But it's essentially like experimentally determined. And what it says is that most molecules, when they collide, that's not the only thing that causes a chemical reaction, right? You can't just expect to, you can't just throw something in something else and they collide and then all of a sudden it occurs. They have to collide within 2 things, 2 main things. 1 is the orientation. They can't just collide arbitrarily. The orientation of the molecules matters. 2 is that they need enough kinetic energy to when they collide. And that kinetic energy we call activation energy. Why? Is because it's the energy that activates the reaction and kind of drives it over that hump, so to speak, that actually causes a particular reaction, okay? So in the Maxwell-Boltzmann distribution curve, molecules with the required activation energy are very few and far in between. That's why there's that small section on the end of the curve. That's when a reaction actually occurs. Most molecules, they will collide, yes, because molecules move a lot. They will collide. However, most of them don't have the required activation energy and are therefore unable to react. Where'd my mouse go? So not all collisions are successful, it's difficult for molecules to react. You might see like a reaction occur that's pretty, like, you think it's pretty simple, but like at its core, it's very difficult for a reaction to occur. That doesn't mean they don't happen. They happen all the time, but it is difficult. Just remember, you don't need to know like the curve. You don't even need to know the name, actually, I don't think. But you just need to know the idea, right? You need to know that when 2 things collide, it's not necessary that they'll react. It's dependent on a lot of different things. Most importantly, 2 things, orientation and energy. Okay. This curve can show up. Okay, thank you for the clarification. So do know, I correct myself, do know the name of the Maxwell-Boltzmann distribution curve and know what it means. Okay. All right. So how does a reaction occur? Generally speaking, reactions pass through something we call a transition state. And what happens in that transition state? If I take a pretty simple reaction, right? If I take the decay is not the right word. If I take like the breakdown of H2O2, hydrogen peroxide, and it breaks down into oxygen and H2O, right? That reaction does occur. How does that happen? Think about that for a second. How does that happen? Does it just occur and does it just randomly just decide to like explode one day into those 2 things? No, right? That doesn't make a whole lot of sense. The reaction, the molecule has to pass through a transition state where it's somewhere in between our reactant, H2O2, and our product, H2O and oxygen, right? In this case, there's 2 H2O2, but like you get the point. So the 2 H2O2, like when they line up, when they collide properly, and they have the correct orientation, and they have the correct the minimum amount of activation energy, they find this state in order for the reaction to occur that we call a transition state, and they reach an activated complex, which is a state where it's not H2O2 anymore, but it's not quite the product. It's literally somewhere in between. Okay. However, since these 2 things have already collided, they have achieved the required activation energy, and thus they have sufficient energy to become a product, right? EA is what we can call that energy required to form that activated complex. So in one of these graphs that you see in the top right, which I know you guys have seen so many times, I just know it, okay? An activated complex occurs at the very top of that like energy, of the potential energy like hump, so to speak. And that means when you've gotten the amount or the required amount of activation energy, then you can achieve an activated complex. You can't do one without the other. Yeah, thermo, exactly. I'm sure you've seen this like 5,000 times in thermo. So, okay, in this example, the graph on the bottom right, or well, the table on the bottom right graph is just generally, it's just a boiled down. It's without like the little hump lines, but it's like a similar thing that you like see on top. There's an energy graph. That's how much energy the molecules have. It's an activated complex that you have to reach, and it's a product that's you have to reach as well. Okay. Don't worry too much about the names. Don't worry about the cis, the trans butene, cis butene. If you have heard it, cool. I'm happy for you. If you haven't, it's not a big deal. Don't freak out. I promise. This is just one particular example of so many things. Okay. So in this example, the activation energy requires, so how much energy do we require? We require 260 kilojoules per mole. So what happens when the collision has occurred such that it has 262 kilojoules per mole? Well, it'll reach an activated complex. Therefore, it'll get over that hump. And in this case, the product, transbutene, is more stable than the reactant by a little bit. And therefore, you can go over that hump and kind of go down the other side, and spending the energy, it releases the energy of 266 kilojoules to go down the other side. That means it's more stable, so it will be thermodynamically favored for transbutene to be transbutene in this case, not cisbutene in this particular thing. However, in just a general reaction, it will be more thermodynamically favored for you to have the product than it will for the reactant. That's why the reaction occurs. That's really important to note. Okay? Just because it releases 266 joules and accepts 262 doesn't mean this reaction is spontaneous. It's not. Right? What that means is that once you've injected, so to speak, once the molecules have achieved the right amount of energy, 262 kilojoules, in turn, they will release 266 kilojoules while going down the other side of that like reaction graph of the reaction coordinate. Okay? And they'll return 266 kilojoules. So your net reaction has released 4 kilojoules. So it's exothermic by 4 kilojoules. Okay? The activated complex, I mean, I think you need to know, I think you need to know how much I've talked about it. I don't think you need to know what it is like organically, especially. Activated complex is a huge thing in orgo. You don't need to know that. So, yeah. And yes, entropy change for this reaction is relatively irrelevant. It's roughly 0. It doesn't really, there isn't one. But in general, you can determine like the entropy based on a lot of other factors that I promise I will get into. Okay. All right. Let's talk more about reaction mechanism. We've kind of covered what they are. There are a series of these smaller reactions that make our overall reaction, and we can boil those down into elementary reactions. I talked about that when we went over those. And all molecular products that have like an elementary step are defined in the rate law. And a rate law for any given elementary step is derived for that step stoichiometrically. And the sum of elementary steps must give the overall balanced equation for the reaction. That is a 100% certified Rahi guarantee. Okay. You need to get the overall balanced equation through essentially add down all of your elementary steps. You can't have extraneous random stuff, because that means either you're missing a step where it's consumed, or you have an extra step where you're like releasing something else that doesn't make sense. But yeah, because you can't have anything that's not already present in the balanced equation. Otherwise, that equation isn't correct, I guess. But yeah. And then over here is just an elementary reaction and their corresponding rate law. Yeah, so you have unimolecular reactants, which are first order, bimolecular, which are second order, different type of bimolecular, where it's not the same. It's not the same type of reactant, but it's two different reactants. But in the end, it's still a second order reaction, right? And then so on and so forth, where you get third order. You can go up to a lot of order. It's not typically, like, it doesn't typically happen, but you can. Okay. All right. Okay. So let's talk about rate law again. This table is something that I've seen a whole lot. It's essentially just a table of it's like an experimental table, so to speak. So you have an experiment, you have two concentrations, one given concentration of A, one given concentration of B, and you have the rate of the reaction, right? You have the initial rate. What is the initial rate? The rate at T equals what? 0. Okay. And you have a couple different experiments where each experiment, they've changed something. And then the rate has either changed or not changed. And through that, you can determine the rate law. Okay. This table is common on the AP exam. Quite. So I would get to know it. And yeah, exactly. Yeah. Kritika is right. You do look at how much the rate has changed, and that's how kind of you determine. So like in like say like from reaction 1 to 2, right? What happened? We doubled A. Okay, well if we doubled A, what happened to the rate? Well, it also doubled. That means with respect to A, if it's only doubling, that means it's first order with respect to A. That doesn't necessarily mean it's first order in general because we don't know that yet. It could be, but we don't know. But in this case, it is first order with respect to A. And then we can look at other stuff as well. Okay. And yeah, so rate laws are determined experimentally. And you use data from various experiments. We, do things with the concentrations where you can look at the reactant rate. And then that's how generally we try to determine the rate law. Yeah, I would say it's definitely more FRQ because this is like kind of I could see it being like you're given this table and then you're given like the rate laws like in like 4 different like multiple choice questions. It's which one's right. Like I could see that being one. But I would say it's probably a little bit more common in FRQ because like you can kind of do the math to let you have when you have to do the math to figure it out, and they do sometimes want to like see how you've done the math. So I would definitely think that that's pretty common. Okay. So in reaction mechanisms, when you have a lot of things going on with the reaction, when you boil it down to what do we call them? Elementary reactions, then we can add those elementary reactions to get an overall reaction, right? And that means that one of the reaction is typically a rate determining step. Now, what is a rate determining step? A rate determining step is one particular step in an overall reaction mechanism in all the steps of a reaction that is slower than the rest. And what that means is that reaction determines the overall rate of reaction. Okay? So in this case, 1 O3 plus iodine ion yields O2 oxygen plus iodine oxidate, maybe? I don't know. IO minus. And that's a slow step in this reaction. The other 2 steps are fast, right? What that means is that the step 1 will determine the rate for the overall reaction because everything's dependent on that, right? Have you heard that like proverb that's like, we're only as strong as our weakest member or something? I don't know. Isn't that a thing? I swear to God, that's a thing. But yeah, like it's like the same deal, right? This is like dependent on the slowest reaction. So what step is the rate determining step? The slowest one. Yeah, weakest link. Thank you. Yeah. So the rate determining step determines the overall reaction rate, and intermediates are produced in one step and consumed in the next, right? Give me in the chat a little interactive moment for you. Give me one intermediate in this reaction, in this like determined mechanism. Give me an intermediate. There you go. Yeah. IO is an intermediate. Yep. Exactly. How about another one? You want to give me another one? Does anyone have a unique intermediate? HOI. There you go. Exactly. Exactly. Perfect. 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 Thank you. All right. Yeah. Okay. Yeah. Okay. I guess to clarify, yeah, I didn't talk about HOI yet because we didn't get to steps 2 and 3, but it is an intermediate. Just because it's a slow or fast step, does not affect if something is an intermediate or not. Intermediate is like its own thing. If it is made in a step, so HOI in this case is made in step 2, right? And that's consumed in step 3 immediately, which means overall, when you're looking at like the overall reaction that's occurred, will you see HOI? No, because it's produced and then used. Okay. All right. Here's a little exercise, I guess, for you. I'm gonna talk about this one. You guys don't have to like do it on your own, but like if you want to, by all means, take your earbuds out or something and do it. It's cool. But the elementary steps of NO2 gas plus carbon monoxide gas yields nitrous oxide gas and carbon dioxide, right? That is the overall reaction. The overall rate law here is dependent on, it's a first order with respect to nitrous dioxide, and it's a first order with respect to carbon monoxide. So in our steps, we have nitrous dioxide gas yields nitrous oxide and then nitrous trioxide. And then our next step in step 2, nitrous trioxide is reacted with carbon monoxide, to yield nitrous oxide and carbon dioxide. You might think this is a little odd to look at. Why? Because there's 2 nitrous oxides in the first step. However, the overall reaction is already balanced, right? There's only 1 nitrous oxide. So why are there 2 in the first step? Well, one reacts, but then 1 is also a product in step 2. So overall, am I using 2 nitrous dioxide? No, I'm using 1 overall, because I'm using 1 and then I'm producing 1. So when you look at the big picture of the overall reaction that's occurred, there's not 2 being used, right? And then also, do note that each step has its own rate law, because a reaction mechanism is a series of reactions. They're not just, these aren't like fake reactions, right? I don't want you guys to get the wrong idea. These aren't fake reactions. There's a slow step and a fast step, but these things do occur, which means if it's a reaction, it has a rate, right? If it has a rate, and yeah, you can't, so determining if a step is rate, like determining which step is rate determining, like if I just look at this, I don't know. But it's experimentally determined. So you guys don't need to know why, or you guys don't need to know which, but you guys need to know like how it occurs and what that means, right? Like if I tell you something's a slow step, what does that mean? So that's what's important in this case. Confused on how to replace the intermediates when you're finding the rate law. So intermediates are used, like I said, if I hop back to this slide for like a quick second here, right? There's things that are like made and then used, which means they're not in the rate law. Exactly. They can be in one given rate law. So in this case, right, if you look at the second step, yes, nitrous trioxide is part of the rate of the second step. It is. You're not wrong. You're not seeing like something wrong. However, overall, is it part of the rate of the reaction? No. Why? Because it's created and used. Okay? It's a little bit confusing. I understand it. Like it's a little bit convoluted, but it's important to understand that. Okay? Catalysts do not appear in rate laws ever. They will affect the rate. But how do they do that? By affecting K. They themselves, since they are never used in a reaction or made, you have the same amount of catalyst as you end with always. That means that it's not ever going to be in the rate law as a concentration of the catalysts. Okay? We're good? We're holding in there? Holding in there? Good. Okay. What is a steady state approximation? Well, a steady state approximation is a way to determine the rate law if the first elementary step is not rate determining, right? That means if we're assuming the reaction has already reached a steady state, we can use the concentration of reactants and products to calculate the rate of the reaction. That is dependent on the equilibrium of reaction. What is the equilibrium again? We talk about this a lot when we talk about gases because it's really important. But in general, an equilibrium is when the forward and reverse rates are the same, not the amount of forward and reverse, the rate of the reaction. Okay, it's not dependent on the amount of product and the amount of reactant. It's dependent on the rate of the forward and reverse reaction. And you can substitute the rate of the fast steps into the slow rate step through the steady state approximation, and we will look into that. Okay. All right, let's talk. So how do we use the steady state approximation? It's a series of steps. It's easiest to break it down that way. So first, what we're going to do is we're going to identify our elementary steps. Okay. In this reaction, we're going to identify our elementary steps in 2 steps. We have a fast step, nitrous oxide makes dinitrous dioxide, I think. And then N2O2 plus hydrogen gas yields water and nitrous dioxide, dinitrogen oxide, right? That's our slow step. What does that mean? That's a rate determining step. So we need to determine our rate law and our intermediate. Okay, so the rate law of our fast step is, this is an equilibrium, right? So the rate law of our fast step is the rate of the equilibrium, the K, which is our rate constant, times the concentration of NO squared, yields or equals the rate of the reverse step, Why? Because equilibrium exists. Why are we setting it as equal? Because equilibrium exists, right? And that's dependent on a different rate, the rate of the reverse reaction, times the concentration of N2O2. And then our intermediate in this case is N2O2. So in order to, excuse me, in order to determine our overall balance equation, we're gonna cross this out. I probably should have asked what the intermediate was. That would have been a good quiz question in hindsight. But the intermediate is N2O2, which means N2O2 is made and then used immediately, right? So that means overall our reaction is 2NO plus H2 plus hydrogen gas yields water and N2O. Okay? Yes, thank you, Yash, for catching that. That is a mistype. Okay. So then we're going to substitute our intermediate into the rate. And here, I'll just put everything on the screen because it's easier for me to talk. When we substitute our intermediate into the rate, that generally just means like we use the thing that's used, we plug it into our equation. The reason it's 2N2 is because, or 2NO, sorry, is because we have to balance the equation, okay? And if we only had one, then how would we have N2O on the other side? That's why. So once we plug it into our rate law, we realize the rate is K times K prime, which is just the K prime is our ratio of the forward and reverse reaction in our fast step, right? So it's K times K prime and then times the concentration of NO squared. Why? Because there's a coefficient 2, which means the order is second order with respect to NO times the concentration of H2 or hydrogen gas. And then what that means is what happens when we have K times K. Well, since K is just a rate constant and K is another rate constant, we have, oh my God, can you guess? Another rate constant, right? We just have a new K. Yeah, so, okay. The coefficient of NO is like 1 in the, or so in the fast step, it would be 2NO. It would be 2NO. Yeah, sorry about that mistake, but just there is a 2NO in the fast step because look at the reaction, right? If you were trying to make N2O2, you need 2NO. So, and the reason this is K double prime is because K double prime is our new rate of reaction. And by plugging it into the rate law, we have K and K prime. Yeah, so you can just write K. So K is just a rate constant, right? And what that means is like, you know, it's just like a regular constant. But like since we have two constants multiplied, we create a new constant. Like it is just K in general. It is just a another rate constant. But we're just using like the little apostrophe. It's like prime, right? We call it prime. And we're just using that to like be like, this isn't the same as the previous K, right? Because if I just wrote K times K equals K, you'd think it's the same thing, and that's weird. But we use K prime and K double prime to just kind of like signify that these are different constants that we're talking about because we did that. Okay. Yeah, we're just trying to make it clear. Exactly. We're just trying to make it clear. All right. So let's talk about catalysis. I think this is one of the last things, right? So you guys are holding in there. Proud of you. Proud of you all. So catalysis is the problem of using catalyst to increase the rate of the reaction. How do we increase the rate of the reaction? What is the best way that a catalyst does that? Well, catalyst lowers the activation energy. It doesn't participate in the reaction. It doesn't have an effect. It doesn't effectively participate in the reaction. It's not consumed by the reaction. You don't ever have more catalyst than you start with. You'll never have less catalyst than you start with. You'll always have the same amount because it's not used in the reaction. And catalysts increase the number of effective collisions or provide a reaction path with a lower activation energy. Both of these things will lower the activation energy. Either the reaction path being the way it progresses, the mechanism in which it progresses, we can change it and like kind of have a different mechanism that maybe has like a different slow step or something like that, right? So we can do that, or we can increase the number of effective collisions. And what that'll do is just generally increase the amount of things colliding, thus increasing the chance of reaching the activation energy, thus increasing the chance the reaction occurs. You guys are like having fun without me. I like Peach Oolong too. Okay? I will have you know. Yeah, okay. Okay. All right, well, guess we're going to stop talking about boba because I'm going to ask you questions and you're going to answer them. So take that. Okay. Talk to me. Explain how the activation energy influences. How does the activation energy change occurrence and speed of chemical reactions? How does activation energy work? What is activation energy? Something. Give me something along the realm of questions. And maybe someone DoorDash me boba. Maybe. I'll give you a second to get your answers in. I want to see a few people talk about activation energy. Okay. Oh my God, there you go. I see answers. Okay. Read some of these. Activation energy is the minimum required energy required for the reaction to occur. Yes, yes, it is. It is. So, how does activation energy work? Lowered activation energy is because of a catalyst. You are also right. A low activation energy will increase the speed of a chemical reaction. It will increase the rate, not the speed, but yes. It will increase the rate of a chemical reaction. Right, exactly. Okay, I'm seeing good answers. Thank you, guys. Thank you. Activation energy is the kinetic energy needed to cause a reaction when two particles slam into each other in the correct orientation. Exactly. Two big things need to occur, right? I told you two big things. One is orientation. Two is kinetic energy. Activation energy, the rate and speed of a chemical reaction is dependent on the activation energy because that is the energy that the molecules need to travel with in order for that reaction to even occur. If the reactions hit each other, which they will and they can, if the reactions hit each other with basically no energy or less energy or not enough energy, the reaction's not going to occur, right? Okay. How do catalysts increase the number of effective collisions? Okay. Danny, you are entering A, you're entering my research. B, you're entering a deep realm of a mess that we don't want to deal with. However, I will say this, okay? Catalysts can do something. Specifically, we don't see this a lot in like the kind of chem that you guys learn because a lot of the chem that you guys do is inorganic. But catalysts can increase the number of effective collisions because collision is determined on two things, right? They can lower the activation energy. This is true. However, it can also change the orientation, right? What if I have a catalyst? What if two molecules need to hit each other head on, so to speak? This is like a very boiled down example, but if a molecule needs to hit each other, like two molecules need each other head to head, but they're hitting each other, like they can hit each other head to tail to tail, not necessarily, off to the side weirdly, right? What if I take one molecule and hold it so that only its head is exposed? Isn't it more likely that another molecule would hit it and it would cause a head-to-head hit and that would cause a reaction to occur? It is, right? That is one of the things that that catalyst can do. That is one of the ways that we don't need to lower the activation energy. However, a catalyst will still cause the reaction to occur faster. Does that make sense? We can orient the molecules. We can force their orientation using catalysts, using molecules that hold them in place, or maybe cover the other parts of the molecule so they don't get hit. And that means that it's more likely to collide in the orientation that we want it to collide, thus causing a reaction to occur. Doesn't really happen in organic chemistry because catalysts like that are like, but it happens a lot in organic chemistry and also in biochem because a lot of the almost every single protein-based reaction in your body occurs like that. Okay. Justice for Rahi indeed. Justice for Rahi indeed. Yeah, it's called stereoselectivity. Thank you for the word. I completely forgot it. All right. What is a rate determining step? Talk to me. How do we find K if the first step isn't the rate determining step? Don't tell me like exactly what you need to do, but tell me what it's like is. Why would you say that? Like, why do you, hold on. There you go. The rate determining step is the slow step. Yep. What technique do we use to find K if the first step is not, though? Riddle me that. Yes, we use a steady state approximation. Exactly. Exactly. Okay. Before I go to the next slide, because I know you guys are going to read it before I finish reading it out loud for you. And then, you know what you guys are going to do? You can put the answer in the chat, and then be good. Don't do that. The next question is a multiple choice question. Do not put your answer in the chat until I say so. Okay? Thank you. Oh my God, there's a little... Wait, how do I turn this on? On both. Really? We were doing so well. Okay, I'm going to read it. In a lab, a student is given 21 grams, a 21-gram sample of pure copper metal. Which of the following pieces of information is most useful for determining the number of atoms in that sample? Assume that the pressure and temperature in the lab are 1 atmosphere, 25 Celsius. It did miss you guys, right? I know, it's back. It's back. Guys, did anyone else like it when Anugo went to go get boba and disappeared for a little? Did anyone else like it? Because I liked it. Yeah, okay. Okay. What am I talking about? Oh yeah, question, steady state. Yeah, we'll go over here. I'll go over steady state one more time, and then maybe we can go over it again in Q&A if people still have like questions. Okay, I will after this multiple choice question. Bear with me, okay? Yeah, anyway, all right. No more samosa. No more samosa. So, what do you guys think? Answer in the chat. You can put your answers in now. Everyone had time to think and answer. And I want to hear what you have to say finally, because I didn't want to hear what you had to say before. A. Lots of A's. Yes. Yes. Oh my God. No. Oh my God. Yeah. The density could be used with a given mass to determine the volume, but that wouldn't be helpful. We don't want to use the density. And also the volume is not exactly given. And yeah, and also isotopes. But yeah, so this is pretty simple. It's pretty straightforward. The molar mass will let you determine. Yeah. Okay, let me go back to steady state. Yeah, I'll keep it all up on screen. I'm gonna go through steady state one more time. Here's like my little schedule. I'm gonna go through steady state one more time for you guys that are like, Rahi, why are you jumping around? Stop being annoying. And then I'm gonna yap for a while, because I don't know, you guys like when I yap. And while I yap, Yasha's gonna get ready to do the quiz, and then he's gonna do the quiz with you, and then he's gonna do the Q&A with you. So if you guys have burning questions that aren't for me, because for some reason, none of the burning questions that you guys have for me, not none, A lot of the burning questions that you guys have for me aren't about chem, but I don't know. I like yapping. I'm a yapper, so I'll do it. But yeah, so we're gonna go through that, and then I'm gonna All right. So let's talk about steady state again. Okay. So steady state, I'm gonna try to put it a little differently for you guys. I'm also gonna clarify the mistake on this slide, so bear with me, please. So I'm gonna try to put it a little differently just so you guys understand. So we have elementary steps. Okay. The steps are, I know it says NO equals N2, or NO goes into N2O2, but balance that. We have one NO and we have N2O2. I don't really make no sense. So what are we gonna do? We're gonna have two NO, and then that's gonna become N2O2, right? That's our fast step. 2 NO, N2O2. Okay, that is a typo. That is a mistake on the slide. That is a typo. Okay, to clarify. And then our slow step is we're going to take N2O2 and we're going to take hydrogen gas and we're going to make water and we're going to make N2O. And that's our slow step. Okay, this is why we need to use steady state approximation in the first place, right? Is because technically we have two steps, which means we have a rate that means a fast step occurs and then a slow step occurs, which means the slow step occurs later because the fast step has to occur first. However, the slow step is still slower, which means it's more rate dependent and it's more effective on the rate than if a fast step was after that, right? That's why we use steady state, because we use steady state so we can approximate and we can get an idea of what our rate law should be when our first step is not the slow step. Okay? You get me? You with me? Good? Okay. So what do? We're going to determine our rate laws for the fast step, for the first step, right? For our fast step, our rate law is going to be a particular rate and then NO squared. Why is it squared? Because there's a mistake. It's squared. That is correct. That's not wrong. It's squared because it's 2 NO. That makes N2O2, right? And that's why it's squared. It's a second order reaction. That reaction is that rate, that overall rate of the reaction, Ka times NO squared, is equal to the rate of the reverse reaction. Why? Because equilibrium exists. So that means that's equal to Ke and the times the concentration of N2O2, right? I will re-explain what happens to K. Bear with me. I will. I'm getting there. I promise. And also, our intermediate in this reaction is N2O2. Identify the intermediate, right? And then we're going to balance our equation. We're going to cancel it out. We're going to get our overall equation. Our overall equation is 2NO plus H2 yields H2O plus N2O, right? Okay. And once again, I will reiterate for like the 50 millionth time that it's 2NO because you need 2NO to make N2 because there's 2 nitrogens on each side. That is when we balance it, okay? That's why it's 2NO. You're with me? Yeah? Okay, good. Okay. So our rate of the fast reaction is equal to Ka, which is the rate of our forward reaction. Our subscripts are not, these aren't different things, right? In the end, everything is K. Our subscripts are just identifying unique Ks, and I'm telling you what these subscripts mean because we're talking about different types of Ks, okay? That's like trying to clarify the questions about like, would I just equal K? Would it just say K for the rate? Would I just say K? It is K. It is just a rate. The reason we're using all these subscripts is because we're trying to signify which K we're talking about. Because if I just keep saying K over and over again, you're going to be like, which K is what? What's the K of the forward? What's the K of the reverse? Because they're different. They're not the same number. They can't be. So you're going to say, you know, we're just using identifiers, okay? All right. So once again, I just lagged when I said what Ka was, really? Oh, okay. Ka and Ke and also K prime and also K double prime are all different types of K, okay? They're not the same number. If I put numbers in this equation, they are not the same number. I'll say that again and again and again, right? They're not the same number. That's why we use different terms. That's why we have subscripts and like superscripts and whatnot. So K equals NO2 equal Ka, times the concentration of NO squared equals Ke, which is the constant for the reverse reaction. That's why we have two different Ks, right? Ka is going forward and Ke is going reverse. That's why they're equal to each other, and then times that. Okay, so then what do? We solve for K here. We're solving for the ratio of Ka over Ke. So when we do that, we can get Ka over Ke, or sorry, I'm sorry. Okay, I'm going to reword myself. We're solving for the concentration of N2O2 because N2O2s are intermediate, right? So we're going to do that, and then we're going to get Ka over Ke, which are, again, two different K, times the concentration of NO squared equals the concentration of N2O2. That's why, because N2O2 is our intermediate, right? So then we're going to plug that into our overall rate law. So then what happens when we plug it into our overall rate law? Then we get K times K prime, which, again, two different Ks, because Ka over Ke is our new K, because it's a ratio. It's still a rate constant, but it's our new K. So K, the original, you understand it now? Thank you, I'm glad. The original K times the new K prime that we determined by doing our substitute intermediate is equivalent to this rate law of NO squared times the concentration of hydrogen, which is from our overall balance equation. But now we have two Ks, and that's kind of annoying because we don't want to write it as two Ks, right? That's why when we do K times K prime, we just make it K double prime. What K double prime is saying is that it's different from K and K prime. This is a different number from both of them because we're doing something. We're multiplying them together. However, it's still a rate, right? So that's why we still make it K, but it's K double prime just to signify the only thing it's signifying is that it's different. I promise. Okay? Okay. Let's go here. Okay, so we finished the checkpoint. We finished the multiple choice. You know what that means? Break. But you know what that also means? Okay, I did talk for a long time, so you guys will get a break. However, we do need to get to this Cram quiz. So how about let's make it a 5 minute. Okay, we want to skip the break? Okay, I lied. I'm going to skip the break. We're going to go straight to the Cram quiz. Let's go straight to the Cram quiz. Okay? Okay. I'll leave it up here, but then I can keep sharing as well for the Cram quiz, okay? I don't mind.
Does your audio work?
You guys heard Samosa over the multiple choice question, right? Yes, I think. So yes. Yeah, the link will be in chat. So I'm gonna put it in chat. Thank you, thank you, thank you. There's also a QR code. Please scan the QR code, and I will switch it to the quiz in just a moment.
Hey everyone, what's up? Back to do the kinetics quiz. So hopefully everyone enjoyed the lesson from my. Everyone should say thank you in the chat too. That's such a good lesson. Ready. Join. Alrighty, let's get started. Alrighty. So it seemed like this question was pretty tricky for us. This is a harder question. So the best way to solve a question like this, where it's asking you to explain a phenomenon, is to eliminate the choices that you know are not correct. So look at A. Lower electron affinity values up the group, promoting faster reactions. That's not true. You know that chlorine is the has the highest electron affinity in the entire group, and bromine is a smaller one, iodine is a smaller one. So that's not a true statement. So you can immediately eliminate A. Electron affinity is the energy released when 1 mole of electrons are added to 1 mole of the element in its gaseous state. You can also look at B, higher electronegativity values moving down the group, enhancing reactivity. That's not true as well, because as you know, when you move down the group, your electronegativity also decreases, right? Again, looking at D, same thing there. That's a false statement. As you go down the group, the furthermost electron gets further away from the nucleus, and that means the ionization energy decreases. So the only real answer left is C, and C does make sense because a smaller size leads to faster reactions. Yeah. Electron affinity is the energy released when an electron is added to an atom. So for very electronegative atoms like oxygen, fluorine, chlorine, energy is released when electrons are added to it. To watch a replay of this stuff, go to your My Stuff tab in Fiveable, and you should be able to watch a replay. All right, seems like you did really good with this, guys. Rahi really explained this one well. For a complex mechanism, the rate determining step is the slowest step. And that makes sense, right? Because, oh wait, replay videos not. I think they'll be up later, if I'm not mistaken, the replay videos. And so going back to this question, that makes sense because, as Rahi was saying, you're only as strong as your weakest link. A chain is only as strong as its weakest link. So that's like a bottleneck. The slowest step is like a bottleneck for how fast the reaction can actually go. All right, let's go to the next question, please. Assume that 2 is an exponent. For the steady state approximation example, could someone please explain how the concentrations change from steps 4 to 5? I'm not sure what you're referring to. Are you referring to what Rahi was explaining earlier in the... Oh, thank you. What the hair. Thank you. Yeah, it doesn't really do much. Like, it only stays flat. All right. Looks like you guys did pretty good with this one. So the important thing to note is that the overall order is the order of each reaction sum of each of the individual reactants summed. So if we have NO2 is 1 and F2 is 2, we have to add 1 plus 2 to get to 3. All right, Vivian, I'll look at your question while we're doing the... Yeah, I am. I'll look at your question while we're doing the next question. So from 4 to 5, which step exactly are you confused about, Vivian? So the rate, Vivian, so the rate is equal to N2O2 times H2, but the concentration of N2O2 is equal to NO2 squared times the constant. So you have to remember to include the H2 in there. Seems like you guys did pretty good on this one. It's also just the natural log of 2 divided by the half-life, and that would give you around 0.012 inverse days. It's really, really important to keep track of your units when doing kinetics questions because they always love to ding you on the units. Yeah, natural log of 2 and 0. Yeah, I think I got it, but natural log of 2 is approximately equal to 0.693. Yeah. If you don't understand how to do this one, there is a formula on your reference sheet that tells you the half-life, the relationship between half-life, rate constant, and the natural log of 2 for a first order decomposition reaction. Yes, it is given on the AP exam. So yeah, let's move on to the next question, guys. Make sure you're watching your units. That question didn't try to get you, but FRQ will. These units of half-lives always days. No, it can be seconds, it can be minutes, it can be nanoseconds, it just depends. Okay, it seemed like this question gave us a little bit more trouble than the previous questions. So for a second order reaction, you can always derive this from the integrated rate law, but for the second order reaction, I'll put it in chat. The half-life, T1 half, is equal to 1 over the initial concentration times K. So when you double the initial concentration, you effectively half the half-life. If anyone is confused as to the derivation of that formula I just put in chat, I can provide some insight on that. I think it's relatively straightforward algebra using the integrated rate law. But I can if you would like. I don't expect you guys to be expected to know these on the AP exam. For the first order ones, yes, most likely you will have to apply those at some point during the exam. But for the second order and 0th order, I don't see you having to apply them. But I could be wrong. You can always derive them. Okay, I'll go to the next question. I think the stream may have ended, Rahi. Yeah, these questions are excellent practice. Exactly, Elias. These are not exactly like AP questions, but they are basically requiring you to take the same concepts and apply them in similar ways, just not the exact same. Just a little bit faster than AP questions. Alright, looks like you guys did pretty good on this, roughly 2-to-1 ratio. So I think no one picked A and B, that's great. So for C, if you change the pressure of the if you change like the pressure of the reacting concentrations of the reactants, you can see what will influence the reaction rate. So say if you double the concentration by doubling the pressure of a certain reactant and the rate quadruples, you know it's a bimolecular collision, right? Because it's a rate order of 2, an order of 2. Similarly, if you like triple the reacting concentration and the rate only triples, you know it's unimolecular, correct? Pressure and volume are always inverse. If you hold volume constant and you double the pressure of a certain gas, you effectively double its concentration, if that makes sense. So if you were to add inert gases without changing reactant concentrations, you are basically doing nothing. You're changing nothing. You can add as much inert gas as you want, and nothing will change. If you look at the rate equations, there's never like an extra variable like concentration of argon over here, concentration of neon over here. No, it's just reactants and sometimes occasionally products. Okay, I think this will be our last question. Let's answer this, guys. Let's answer this quickly, guys, so we can get to our Q&A quick. will we get to do practice FRQs at all during crams? Yes, especially the last day of crams, we'll be doing a lot of practice FRQs. Yes, you can do a couple buffer FRQs on the last day, but I recommend that you don't spend a lot of time focusing on buffers because since they take up so much time, they are not really tested heavily on the exam. Alright. Great job, guys. 90% if you guys got this one right. So, of course, as temperature rises, you have more kinetic energy. Going back to that Boltzmann graph, the distribution of particle energy, you will have more particles that are past that activation energy barrier and can therefore overcome the energy of activation for the reaction and actually undergo the reaction. Yep, okay. So that should be it for the quiz today. Let's do the Q&A. So just all your questions, send them over. Is it possible for you to explain the question before on the cram quiz? Which question are you referring to? The second to last? Let me. Are you talking about what variable must be altered in order to distinguish between an elementary? Sorry, this one? For the steady state approximation, why is it fast step for rate law and not slow step? So it is slow step. I'm not sure where you're getting fast step. You can use the fast step to determine concentrations that are in your slow step, but it is, in fact, the slow step. You want to look at number 6 again? When you change the total pressure of the system, while keeping volume constant, you are effectively changing the concentrations of the reactants, which will influence the rate of the reaction in different ways. So, for example, if you double the pressure of the vessel while keeping volume constant by changing the reactant concentrations, and the rate quadruples, you know that your reaction is second order, right? It's a bimolecular reaction. But say you double that concentration by doubling the pressure, and the reaction only doubles, then you know the reaction is unimolecular in first order. Okay, what's the next question? I did orgo second. Okay, how would factor, concentration, temperature, surface area, catalyst affect the rate law and why? So none of those factors actually affect the rate law, except for catalyst. Catalyst can sometimes be included in the rate law, but you generally will never see that in AP Chem. Concentration is part of the rate law, remember? It's actually explicitly in the rate law, like K times concentration of some reactant. Temperature will only affect that K value, the constant, rate constant. It will not actually affect the rate laws the way it looks itself. Surface area, again, that affects K and is not part of the rate. How does the ideal gas law? What was the thing you said about inert gases again? So inert gases they don't do anything. If the volume's held constant and you add a bunch of inert gases, they're not going to change a single thing about the system. So yeah. You can add as much neon, argon, helium. It's not going to do anything. Unimolecular, one atom or one molecule reacts. Bimolecular, two molecules come together and react. The ideal gas law, how does it interlink with kinematics? So kinematics is very separate. It's physics. Maybe you mean kinetics. Yes, questions can mix between those two topics. Really, you just have to know how increasing pressure or increasing volume or whatever, how does that play into the concentration of the species? A steady state approximation often on the exam. I can't imagine it taking up more than 1 or 2 points, if any. Oh, so by altering pressure while maintaining V, you alter concentrations, which is how you can use the rate laws to compare and find the orders. Correct. Yes, that is exactly correct. That is yes. All right. So we are done for tonight, unfortunately. If you'd like to come back, we really encourage you. My AP Chem score, I also got a 5. You can Google my name with AP Chem. Okay, so for question which was 11, how did people get 22.4? So 22.4 is what you get with a 1-to-1 mole ratio, and it's actually a 1 to 0.5 mole ratio, or a 2-to-1. Okay, yeah. So I think we're done for tonight. Yeah. Thank you guys for all showing up, and see you next night, tomorrow night. Yeah.
All right. Let me finish up with you guys, okay? Thank you guys for here. I'm just going to mention a few things before you guys leave. Or, I mean, as you guys are leaving. But yeah, do follow us on socials. Keep updated with like everything going on with us. Thank you so much for joining. This is our schedule once again, okay? Today was our May 2nd. Today was our 4th and 5th. Tomorrow we're going to be doing units 6 and 7. I will be there. I will be talking. Hope you guys like that and continue to like that. So, yeah. But yeah, we will see you tomorrow night. And thank you guys for being there, okay?